One of the first recorded mathematicians of his time, Thales was born around 600 BC in Miletus, what is now known as present-day Milet, in Turkey. He was not only an accomplished mathematician, but also a great philosopher, being one of the first to engage in scientific philosophy. Thales' accomplishments, while hard to exactly verify because of the age he was born in, are very numerous. He generally has 5 theorems attributed to his name. First of which is that any circle is bisected by its diameter, that any isosceles triangle has 2 equal angles, that the angle between 2 intersecting straight lines are equal, so these 2. 2 triangles are congruent if they have exactly 2 sides and 1 angle in common, so these 2 would be considered equal. And finally, and is most famous, is that in a circle, if you form a triangle with the 2 points of the diameter and any other point on the circle, this angle right here will be right angle. Now this is all well and good. We can't really verify if he was the first to discover these, but he was the first to recognize the importance of scientifically proving them, which is pretty outstanding, as this is one of the bases of math as we know it now. But his 2 most important accomplishments were his measuring of the pyramids and his prediction of the eclipse. So when Thales visited Egypt, he was there to study geometry and its relation to the world around us. Now, when he came to see the pyramids, him being a little guy right here, he was kind of wondering, how tall are those? So he went to a royal guard around and he asked, how tall are the pyramids? And of course they refused to tell him, as it was considered a state secret at the time. So he went about trying to devise a way to measure it himself. Now, he didn't really have the modern day tools that we have now to measure something like this, but one thing he did notice is that the shadows that objects casted grow proportionally to the angle of the sun from them and the time of day. What he noticed was that the shadows grow proportionally to the object as the time of day goes by. Now eventually he saw that the sun would reach a certain point where the length of the shadow actually equaled the height of the object, kind of forming a triangle like this. And he figured that it was like this for any object. So what he did was put a stick in the ground, waited for the shadow to be the same as the height, and then calculated the same thing for the pyramids by first measuring the shadow. But the shadow is also obscured by basically half of the pyramid. So he added the length of the shadow and half of the base of the pyramid to calculate the height. Now his figure, while it's kind of hard to verify how close it was reported to be pretty close. So yeah, a lot of this uses similar triangles, which, that's a very well studied thing today in geometry, but back then they really didn't have a concept of this, so it's actually pretty amazing that he was able to find something out like this. Now his other accomplishment was very kind of closely related to this. He predicted within 4 years the date of an eclipse. Now that might not sound as interesting as you think, but let's think back. This was 600 BCE. Most eclipses were seen as forces of supernatural or an omen of some kind. So for him to be like, there'll be a eclipse within 4 years from now, like that's very impressive. And sure enough, a year after making that claim, in 585 BCE, a very well reported eclipse happened. It was reported in many philosophers' writings, including Diogenes and Xenophanes, and most famously Herodotus, who wrote about the battle between the Lydians and the Medes, that actually stopped the battle that day when the eclipse happened. The rulers met and a treaty was signed for a 15-year war. There's not really much understanding to how he predicted this event, and no other Greek scientist or other person really predicted something in a similar manner. But still, the fact of the matter is Thales was a very accomplished and famous mathematician for a reason. He had these events behind him, he had these theorems to his names, and overall he's seen as one of the fathers to proof-based mathematics.
Archimedes was born in 290 BC in Syracuse, Sicily, to an astronomer named Phidias. He is most well known for the physical law of buoyancy, also often referred to as Archimedes' principle. It states that any solid partially or completely submerged in a fluid is acted upon by an upward force which is equal to the weight of the fluid displaced by the body. So, to show this, essentially what that means is, should we have a hanging weight here that weighs 7 pounds, and then we dunk it into the water, obviously water's going to run out, and the scale ends up reading 4 pounds. Then the amount of water displaced over here is going to be 3 pounds of water. And also, a buoyant force acts upward on this weight equal to 3 pounds. That's why the scale reads 4 pounds. Now there are several different theories on how he discovered this, but the most popular one is about the king's crown. Now King Hiero had a crown that was allegedly made of pure gold, but he questioned whether or not it had some silver alloy in it. And he asked Archimedes if he had any way of figuring that out. And Archimedes had no idea what to do. He was stumped. Until one day he got in the bath, and it overflowed as he stepped in. And he had a breakthrough, and he ran home naked, shouting Eureka, because he had discovered the physical law of buoyancy. So basically what he could do is he could dunk the crown in a thing of water, along with a block of gold weighing the same amount. And the difference in displacement of the water would indicate a difference in density between the two metals. While he is revered as a great mathematician, many of his most notable feats were actually inventions, although he himself felt that his machines were far beneath the dignity of pure science. Among these inventions were the Archimedean screw, which is a method of transporting water uphill. Originally invented to remove water from the hull of a ship, it had far-reaching implications for farm irrigation and even reclaiming flooded land, and it's still used today, actually. The way it works is there's a screw set inside of a half or full pipe, and as the screw spins, the shape forces water to travel up the treads of the screw. Also of note were his war machines, as they were called, which he created towards the end of his life when Syracuse was under siege. And they were actually so effective that they managed to extend that siege by 3 years. One of the notable ones was the rumored burning mirror, which was able to light Roman ships ablaze from bow range. When Marcellus's army finally breached the walls in 211 BCE, Archimedes was killed. He was said to have been drawing a mathematical figure in the sand when a Roman soldier ran him through with a sword. It's a fitting end. Not much is known about the life of Euclid because almost nothing about him survived the wear of time. Not even a picture of him, so any pictures you'll see of him are actually just artists' renditions. But he is still known as the father of geometry, due primarily to his textbook, which is named The Elements. Now the Elements drew from the work of other mathematicians, namely Hippocrates and Thales. But Euclid is credited with organizing all of this work into one consolidated place, which is a huge deal. It's considered one of the most important math textbooks of all time. And the topics covered ranged from geometry to number theory, and he instituted a very rigorous method of proving things mathematically that had never been seen before. And that's the most significant thing to come from the Elements. Now we don't have time to cover everything that he did, but one very apt thing is his proof of the Pythagorean. Okay, so this is going to be Euclid's windmill proof of the Pythagorean theorem from his textbook called The Elements. So the first thing we need to do is we need to draw squares on the sides of this right triangle. So I'm going to do that quickly. Okay, so now that we have that, we just need to draw one more thing in, which is a line right here down to the base. And this line is parallel to these. And now we're going to write in a couple points. So, or label all the points with names. So we have E, F, D, I, H, J, and K. And G is right here. So, now, it should be clear to see that this is a right angle because it's a square, and this is a right angle right here. So that means that if we add angle ACB to either of these angles, we end up with the same angle. So this whole angle right here, which is angle IAB, is equivalent to this angle right here, EAC. And then also, side AE is equivalent to side AB, because this is a square, and side AI is equivalent to side AC, because that's a square. Now we're going to draw in two lines from I to B and from E to C, which will create two separate triangles. So I'm going to do that quickly. Okay, so now we have two triangles, one shaded in blue and one shaded in pink. And now because these triangles have two sides that are equivalent on either side of their angles, they're congruent. So triangle BAI is congruent to triangle ACE by side angle side. So this is the first step that's a little bit confusing. Basically now we know that rectangle AGFE here is equal to 2 times the area of triangle ACE. Now this is because of two theorems. The first is that all triangles with the same base and a third vertex right here along a parallel line to the base have the same area. So that means the triangle ACE, the pink one, has the same area as triangle AGE, which is very clearly half of rectangle AGFE. So the area of rectangle AGFE is equal to 2 times triangle ACE. So now we can also use the same theorem up here with this triangle, because this base is parallel to this line, and we see that the area of the square ACHI is equal to 2 times the area of ABI, or rather BAI, because that's what we called it before. So I'll write that down. Okay, so now, since we have that these two triangles are congruent, we can substitute back in, and we find that the area of the rectangle AGFE is equal to the area of the square AIHC. And that's the first part of the proof. Now I'm gonna redraw this, and we're going to do the same proof, but with this rectangle and this square. Okay, so now that we've already done this once, we're gonna go through it a little bit faster. Again, what we're doing is we're trying to show that the area of this rectangle is equal to this square now. So in the same way as before, we know that this is a right angle and this is a right angle. So this angle here is gonna be congruent to this angle. And again, this side of right there is congruent to this side, and CB is congruent to BK. So that proves that when we draw in lines from C to D and from A to K, the two triangles that are constructed are congruent. So I'm going to go ahead and draw and shade those in now, and then we'll finish up. So now that we've drawn those in, it should once again be clear to see that these two triangles are congruent by side angle side, in the same way as before. So we have triangle CBD is congruent to triangle AKB. Okay, so now once again, by the same theorem, it's clear that the area of GBDF is equal to 2 times the area of CBD. So I'll write that down. I'm just going to shorten area with A of GBDF is equal to 2 times triangle CBD. And once again, the area of CJKB is equal to 2 times the area of triangle AKB. Okay, so then once again, it's clear that the area of this rectangle is equal to the area of this square. So I'll write that out. So area of the rectangle GBFD right here is equal to the area of this square, CJKB. Okay, so now we have that and what we originally proved, which was that the area of AGFE is equal to the area of AIHC, which once again is these two. So now what we know is that the area of this whole square here is equal to the area of the two rectangles added together. But we can substitute in for the two squares. So that means if we name these three sides, just to make it a little bit simpler, we're going to name them based on the name of the angle that they're opposite of. So this is C, so this side is named lowercase c. This angle is B, so the side opposite is named lowercase b. And this is A, so the side opposite is named lowercase a. And then if we substitute in, we know that the area of a square is side squared. So C squared, the area of ABDE, is equal to the area of these two squares added together. So that's A squared plus B squared. And that's Euclid's windmill proof of the Pythagorean theorem.
We just discussed the Pythagorean theorem, but how much do you know about the man after whom it's named? As it turns out, Pythagoras was a mysterious and secretive man, so it's hard to say for certain who he really was or what he actually discovered. He lived in Samos, Greece, and is estimated to have lived around 570 to 495 BCE. But none of his own works have been recovered, so everything we know about him is from the writings and the perspectives of other people. This makes it difficult to separate what truly happened from what his followers have romanticized about his life. What followers am I referring to? Pythagoras was the founder of a secret society called the Pythagorean Brotherhood, which was a combination between a mathematical and a religious sect. The Pythagoreans saw Pythagoras as superhuman and believed in his enlightenment so absolutely that Pythagoras saying something was justification enough that the statement was true. It was also rumored that Pythagoras' biological father was the god Apollo, so for his followers he was the connection between the mortal world and the divinities. Everything his followers accomplished they attributed to Pythagoras, because in their mind, without his wisdom and his influence, they never would have succeeded at all. This is a huge part of the uncertainty of Pythagoras' own accomplishments. Just like any other religion, Pythagoras and the Pythagoreans followed a set of guidelines in order to live the most pure life they possibly could. These philosophies included, but are in no way limited to, never harming or killing an animal that does you no harm, and therefore never eating meat, living communally, and avoiding beings. In being a secret society, the members also had to preserve the secrets of the Brotherhood. Because of this, individuals wishing to become members of the Pythagorean Brotherhood had to endure a long probation period to test their dedication to learning, adhering to the lifestyle of the Brotherhood, and their ability to keep secrets. If at any point during the probation period the new member was determined to be unfit to be a brother, anything he had given to the community would be returned to him, a gravestone would be erected, and he would be effectively dead in the eyes of the Pythagoreans. If he were to ever encounter a brother after this point, he would be treated as if he was a completely new person, because the probationary member that the Pythagorean knew before is dead to them. The members of the Pythagorean Brotherhood were separated into two groups, the Mathematicoi, or the learners, who followed Pythagoras for his mathematical and scientific work, and the Acousmaticoi, or the listeners, who followed him for his spiritualistic and ritualistic teachings. Despite this separation, Pythagoras and all of the Pythagoreans believed in the divinity of numbers, that numbers are everything. They built the foundation of number theory and noted several properties of special numbers, like square numbers or perfect numbers. They discovered that the sum of the internal angles of a triangle is always equal to 180 degrees, and that the square of a number, n, is equal to the sum of the first n odd numbers. However, their belief system was based upon the idea that anything can be represented by an integer or the ratio of two integers. We know now that that's not always the case, and this is because a Pythagorean named Hippasus tried to calculate the value of the square root of 2, which is the length of the hypotenuse of an isosceles right triangle in which the other two side lengths are both 1. His realization that the square root of 2 cannot be represented as the ratio of two integers shattered the entire belief system of the Pythagorean Brotherhood, and poor Hippasus was drowned for sharing this information with the rest of the world. Returning now to the Pythagorean theorem, there's evidence to suggest that Pythagoras was not the first person to discover this result. Ancient texts show that the Egyptians and the Babylonians may have also been aware of this relationship between the side lengths of a right triangle. Due to his immense following, however, Pythagoras' name is the one that has been repeated the most and therefore has stuck to this particular theorem. It's not that he said it first, but with the help of his great following, he said it the loudest.